Uh, Hi, Sagnik and Amitalok. Thanks for making this version of the slides. Here's my feedback. All right. So first of all, introductory slide. I'd suggest something like this, a slide that Ihan made. So the title, the name of the presenter, and then photographs of the people present, like the co-authors with contact information, logos of the thing, logos of the corresponding institutions, date, and so on. So these slides may end up online. So you want the first slide to convey all the information that's relevant. Okay. All right. So okay, so you're jumping straight into your first slide is already a technical slide. That's fine. So consider the stochastic BSEP. So you have a message encoder, decoder, and so on. So this is good. You have the rate curve. You have random noise. This is Bernoulli P. Okay, fine. So this is mostly good. I would maybe label this as the message, M as the message, X as the code word, Y as the received vector, S as the state / jamming vector, and then M hat as the decoded code word. Like maybe in a different font, maybe so it isn't too distracting, and also use overlays. So expose each of these things step by step. So Alice has a message. So initially, just this part is visible. Alice has a message M. She encodes it to a code word X. This becomes visible. Then some noise gets added. In this case, the channel behaves like this, and so on. So overlays are quite useful. Yeah. Okay. Next. Okay. Omniscient adversary model. So this is good. So you have a adversarial BSCP. So here you would label that the Hamming weight of S is at most NP, just to be clear what that P is doing, and then explicitly highlight. So maybe put like a red box over here or something saying, around these arrows showing that that S can depend on M and X, right? And instead of the EB bound, maybe call this the LP bound. I mean, it's got a slightly different shape, but you want to present the tightest bound known in general, right? So doing something like that. Okay, and then so the other thing you want to highlight is this arrow over here showing that there's a difference in the gap. In fact, for all values of P between 0.5, there's the difference in the capacity. All right. Okay, yeah, you say that verbally in an overlay, so that's good. All right. So how do you get the rate back up? So that's okay. That's one way of saying it. That's fine. Yeah. So I would just say it slightly differently. Instead of saying how do you get the rate back up, I would emphasize it as like the presence of a small amount of an additional resource, common randomness, can in fact help circumvent this adversarial power. So the adversary is in general stronger, but if there's some separate resource available, common randomness, and in fact the capacity can go back to being like this, at least in the common random, like in this binary, in this BSC case. So that's what we're going to be talking about. So so how much common randomness is needed to get back to capacity? And the other follow-up question I would say is not just achievability converse, but actually you generalize it to general to fairly general channels. So I like that is the context of this talk. That's what you want to be talking about. And just verbally, like when you're doing a practice run, you should be timing yourself. So by the time you get to the two questions you address in this, like how much common randomness is needed, achievability converse, and doing it for general channels, that like that should happen at around maybe the 4-minute mark or something like that. Right? So time yourself on that. Oh, right. You also say for more general adversarial channels. Maybe merge this with the previous slide so that the two bullet points corresponding to what the contributions of this work are presented simultaneously. All right. So the setup, the message, the code word, and the code book are all known to James. Okay, that's fine. Um, uh, so actually, well, let's be careful here. So this is true from an achievability perspective. From the converse perspective, James doesn't need to know the message. He still needs to know the code word, but he doesn't need to know the message. You can prove. Wait, is that true? Like you have a converse against average probability of error as well, right? Uh, like there are even if there's stochastic encoding present, you still have a converse, I believe. So yeah, so the converse, the message doesn't depend on it. I mean, it's a subtle technical point. So, but still, like from the achievability perspective, you prove the stronger thing where it's a maximum probability of error. The converse perspective, it's an average probability of error. So you have something like that. Um, all right. Uh, okay, input constraints, and then here you have common randomness unknown to James, and then you have these state constraints. So since this is quite abstract, it might help to show the example of the adversarial BCP to show them to show the audience what examples of this are like. Like for example, maybe the code word being transmitted is of Hamming weight at most NW. The jamming state is at most NP. The common randomness is maybe a certain number of bits, and so on. So just giving examples of what those things could be like. So flashback to an example that's already known. All right. Um, yeah, I would. Uh, Okay, so be careful about calling this James omniscient, because if there's common randomness that he doesn't know, then James is not omniscient in such a setting, right? So I would just call James a malicious adversary who, based on his knowledge, in this case the code book, the message, and the code word, is going to choose a jamming vector to attempt to disrupt communications. Okay, so and again, state deterministic S completely specifies the channel noise and is memoryless. So again, give an example. So y is x plus s. So yi is xi plus si. So that's why it's memoryless, because the ith channel output depends only on the ith channel input and the ith state thing. And verbally mention examples of channels which are not memoryless. So don't call it memoryless. Memoryless makes people think that of DMCs. So maybe call it symbol wise. So yi is a function only of xi and si. So even though the state vector can be chosen with memory, but the channel output depends only on that state input and the channel input. So the channel operates on a symbol by symbol level, right? And it's state deterministic. So y is equal to xi plus si. That's a function. And in fact, you can generalize this to non-state deterministic things as well. But just to keep things simple, right now you're going to focus on state deterministic channels. All right. Okay. So now you're going to focus on adversary weakened channels. So what are adversary weakened channels? Those where the randomized coding capacity, that corresponds to the capacity that with common randomness is greater than the deterministic coding capacity. And an example of such a thing is the BSCP, as we already know. Oh, by the way, you should reference. So when you first talk about common randomness, like maybe over here, well, maybe not here, but um, let's see. Yeah, so when you talk about this thing here, so common randomness. So the common randomness capacity has been examined in the context of AVCs, and the capacity is known, due to Chizar-Narayanan. Like write down the expression for the common randomness capacity over here. Wait, Chizar-Narayanan, or who was it? Like maybe Al-Swidi. Anyway, look up the corresponding reference and post it over here. Like this capacity is known. Um, whereas like the capacity, and maybe you want to highlight the fact that the capacity without common randomness is in general not known, but known certainly to be smaller than the adversarial capacity, right? So you've already made that point over here for the BSE, but you want to make the point that one is completely known, the other one is not known. So you want to highlight that over here. Okay, coming back to where we were. So you were talking about yeah, just the setup, and then this is your master slide. So yeah, okay, fine. Amit Alok has already given you comments, so I guess you'll be editing this. So here you'll talk about this tuple defining an ABC. So you'll have notation corresponding to this as well, like lambda s, lambda x, the channel, and also the amount of common randomness, right? Because in your case, that will also be a parameter, the amount of common randomness available. So okay, here you have references. By the way, when you give references, oh, there's a typo here. This should be Al Swede. Yeah. So when you give references, you should put them in the there should be a references slide at the end, or maybe there should be small references at the bottom, because again, these slides may be available, maybe downloaded by other people later. So think for posterity, not just now. So 2 log n bits are sufficient due to this, but method not directly applicable for omniscient AVCs. So Amit Alok should check was like whether it was specific, it was exactly 2 log n that Al-Swede used, or was it some other order log n? Should check. Okay, I'm not sure it was 2 log n, but again, just check. So order log n bits are sufficient. So bits are sufficient. Instead of saying this, I would say order log n bits are sufficient. And yeah, so that's fine. Again, I would repeat, or omega log n bits are necessary for binary AVC with bit flipping adversary. So I would call this an adversarial BSCP, because that's the notation. That's the notation that you used in earlier slides, right? And the same thing here. Instead of binary AVC with bit flipping adversary, I would call it an adversarial BSCP. Okay. So that's how I would modify this slide. Okay, sufficiency. So here I would just say, so for any epsilon greater than 0, 1 plus epsilon log n bits of common randomness achieves capacity. 1 minus epsilon log n bits of common randomness are necessary. So instead of putting it in words, you can be more precise here. 1 plus epsilon log n, 1 minus epsilon log n, right? So that's our contribution for adversary weakened AVCs. Oh, actually, you should also, so when you're talking about adversary weakened AVCs, you should also give examples of AVCs which are not adversary weakened, just so that people understand them. Like a simple example where the state vector doesn't impact the channel output at all, like that would be an example of a non-adversary weakened AVC, right? So you should do that. Okay. Okay, achievability. Achievability under a maximum probability parametric. You want to do this. So two-step process achieves it, divides the effort. Like maybe this is best done on the next slide instead of talking about the list decoding and then disambiguation. So maybe just wait until the next slide. I would remove this sentence here. Okay, so it's a divided. So it's a two-step process. So first you list decode, and then you disambiguate using polynomial hashing. This, like, instead of putting this in text, I would verbally say this. This takes too long for the readers to read. So yeah, in general, like you want your slides to be as clean as possible. There to be minimal text, like the stuff on the slides should be as far as possible just pictures like this, rather than text that someone has to read. The more time someone spends reading text on a slide, the less they're listening to you. So you want to be focusing on the text over there, right? This also shields info from the adversary. I'm not sure what the point is over here. Yeah, I just don't understand this. I guess I'll understand the next version of your slides when you give a presentation. Okay, so Alice's encoder takes the message and the common randomness, generates this blah blah blah. So, oh right, so you have 1 plus 3 epsilon by 4, 4 by 4 login. Okay, so yeah, you could. Uh, um, so yeah, I didn't understand why you do precisely 3 chunks. Uh, like I would do it in the following way. I would first give the example where it split this common randomness into 2 chunks, then describe how to split it into 3 chunks, and then say, well, in general, there's a certain you can split into a certain number of chunks, and that's how you get the limiting performance. So they're splitting into 2 chunks. In some sense, that's related to the Al-Swidi work, where you can use a common randomness in a certain way, and then use that with 2 log n bits of common randomness to be able to disambiguate. So first give the idea of how to do it without the 2 log n, like without getting to 1 plus epsilon log n, and then say, well, actually, just instead of splitting it into 2, if you split into more and more pieces, then you get better and better things. Okay, yeah. So again, like here, this is tied to the specific choice of splitting you know the message into or the key into 4 chunks. That's why you have a 3D array. Instead, you would start off with a 2D array, and then sorry, you would start off with just a vector. Then the next thing, when you split into 3 chunks, then you would have a 2D array, and then people can understand in general you want a k minus 1 dimensional array, right? So, but all of that I would do at the next level rather than at this level directly. So yeah, similarly, I would change the hash to describe what's happening over here. So, uh, so transmitted code word is the message hash pair. Uh, I'm not sure what this means. So, transmitted code word is the message hash pair. That's not really what we're doing, right? The code word. So let's see. So ki k1 plus k2. So okay, wait, let me just go down and see what's going on. Now that I don't think that's really what's happening. Like write down the so here you have a hash. This hash is okay. So how do we use the common randomness? So you have k0. Okay, wait, let me just think about. So when you have two pieces of common randomness, you require that k0 plus k1. Okay, I see. Right. So you generate a hash. Let's call it a h or something, and then what you transmit is the hash comma the original code word, the hash of the code word. The hash of the code word time wait hash of the code word or hash of the message oh sorry hash of the message and the code word. So you want to say that you're transmitting x of this plus the corresponding hash over here, right? So yeah, so this is misleading. So I would say that you take you take the h comma x pair and you transmit them together over here, right? So I would say it like that. Um, yeah, I would remove this box r equal to rate. That's I mean that's not really uh, that's I mean if you have r equal to rate here, you may as well put n equal to the block length and then gamma equal to whatever. But that's misleading. Like the actual objects that correspond to things are like there's a message with a certain number of bits, there's randomness with a certain number of bits, there's an encoder which takes a certain number of bits, generates a certain number of other bits, there's a code word. So each of these has some physical meaning. The rate is some abstract number that you're dealing with. So anyway, I'd remove that box over here. It's here and on the other side. It's just distracting. um, Try to so whenever you change the shape of your system diagram, it becomes trickier to digest. Like try to use the same shape that you use everywhere. So in particular, like if your system diagram looks like this, then keep this maybe in reduced size, like so take this shape, maybe reduce it in size, and then if you want to describe the decoder at some point, or initially when you want to describe the encoder, so imagine taking a reduced version of this, putting a small oval around it, blowing it up, and then describing what's happening within the encoder, right? Similarly, taking a blown up version of the decoder and then describing what's happening over there. So here you want to let's see, down here you want to describe the decoder. So describe this as a blown up version of something like that. And uh, all of this can be said in words. Like instead of writing the words here, I would write the equations over here corresponding to what you're doing, just for the just for the two chunk case. And again, like the general version, you would describe somewhere else. Right? Yeah, right now the comments I'm giving are with respect to a time unrestricted talk. Eventually, you'll have to decide what to cut. But first, create the slides necessary for the setting where there's no time restriction at all, and then we can decide how to cut appropriately. Okay, so yeah, analysis. Um, yeah. Um, Yeah, so there's actually more to the analysis than this, right? You have h is equal to this. Now the adversary changes the hash, he makes it some h prime, and he changes the m's to some other things. And again, it's easier to see with just a single polynomial instead of a trivariate polynomial. And then you take the difference of those two. So now you have the short-zipper lemma and so on. And in the general carry case, you have a k degree, k minus 1 degree polynomial, and then it's similar over there. So there you have the short-zipper lemma. So so that's what I mean. That's the level at which I would try to describe the analysis over here. Okay, so just be a little bit more detailed, I guess is my point. Okay, the converse, average probability of error criterion holds even if he doesn't know the message. It's a strong converse. Okay, two parts to this. Rate converse, yeah. So rate converse, even with unbounded randomness, rates more than capacity not possible. This is just because of information theory. I assume that's what you'll say. And then the main part that you're going to, and that's already known because of Al-Swedi. So here you're going to be focusing on the randomness converse. So at least 1 minus epsilon log n bits of common randomness are required for the capacity. So again, this in words is too wordy. You should say like size of r, like absolute value of r greater than 1 minus epsilon log n. That's what you want to be focused on. Right, so so confusability, right, so if there are adversarial actions that can lead to this that can lead to different code words to the same y, then you have an error. Now instead of saying think about the bit flipping case, like again, you want to use the same notation. So adversarial BSEP. So instead of saying that, so the audience hasn't seen that. So you actually have to, most of them haven't. So you have to give more details. So you have to say something like generalizing the notion of Langberg. So if two different code words under different adversarial actions can result in the same y, then that leads to an error. Uh, we can show there are many large subcode books. Okay, so here it's more than that. If they're confusable and they correspond to the same key, right? So you have to show the action of the key. Like otherwise, this is an incomplete picture. It's confusing. You have to argue that xi, si, and xj, sj, and under many keys, they result in the same y's. Then there should be an error. So um, so then here, like basically the converse proof uh, is very high level. uh, yeah, so the converse proof, you're giving less details, whereas that's really what took maybe more of our time and effort, right? And it'll take more of the time and effort of the audience to also understand. So uh, so pick a large subcode book. So maybe so maybe first of all define what it means to be a large subcode book. Like give some numbers corresponding to this. So if you have a rate 2 to the nr, uh, uh, there are 2 to the nr messages. So how large does a code book have to be for it to qualify as a large subcode book? In fact, what is a subcode book? So subcode books are those things corresponding to fixed values of the key, right? So corresponding to those, like, so there are certain subcode books which have to be large. This is just because of counting argument, and since it's just a counting argument, you can actually show that in the slides. It's just 1 or 2 lines, and yeah, many of these steps you can actually you can do explicit calculations to so these words should be said verbally, and then corresponding to that, you should be describing the, like on the slide there should be the corresponding math over here. Okay, so and forget the common one. Yeah, I'm not sure I really understand this. I'll have to wait until I see your oral presentation, like a recorded version of your oral presentation, before I can give some comments on this. But basically, my feedback on this is try to be more explicit. At this point, I'm having trouble remembering how the converse proof went, and the audience would certainly have that as well, because mostly because of the lack of common randomness and the in these slides, and also because of the lack of details in the slides. Um, all right, so a summary again, it should be in, like, phrases, not sentences. It should be uh, uh, as far as possible. In fact, it should be pictorial. So greater than 1 plus, so less than 1 plus epsilon log n bits of common randomness suffice. So less than equal to 1 plus epsilon log n, and then a large tick mark, maybe green color. Greater than 1 minus epsilon log n, and then you put a cross. So necessary and sufficient, or maybe a upward going arrow for the converse, a downward going arrow for the achievability, and then like imagine a graph where the y-axis is the amount of common randomness needed, and you're basically showing that just around log n. So 1 plus epsilon log n is good, so you put a tick mark above that line, and below 1 minus epsilon log n, it's not possible, right? And for general ABCs. So that's what you're able to do. Okay, so that's your contribution. Okay, that's good. Okay, so those are my comments.